Hi, this is Professor Stugard, and in this video we're going to discuss dot products. So what we're trying to do with this video is just understand how to compute a dot product. That's really the most important part, is that computational part. How do I do the procedure? I also want to talk about a little bit deeper meaning or the deeper knowledge behind what a vector is and why that might be important. And then I also want to talk about the dot product theorem very quickly. So first of all, the dot product, how do we compute it? How do I actually find the dot product? Well, the dot product is also sometimes called the inner product or the scalar product. And the way we find it is that we take two vectors, we multiply their corresponding components together, and then sum the results. So here's what the process looks like for finding the dot product between two vectors. So again, we're going to multiply the corresponding components. So for example, my first two components are the 7 and the 1. So I multiply those together. 7 times 1 is, well, obviously going to be 7. And then we do the same thing with each of the other sets of components. So the negative 3 times the negative 4, which would be 12. 0 times 9, which is 0. And then we add those all together. So 7 plus 12 is 19. So the dot product of these two vectors is the number 19. So what you really want to notice here is, again, the dot product of any two vectors is just that scalar quantity. The dot product of two vectors is no longer a vector, it's just a single numerical value. So we started with two vectors, I took their dot product, and my answer was just a single scalar. Now, obviously, if I have to multiply the corresponding components, my vectors have to have the same size for me to be able to find them, right? In this case, both of them had 3 components. So to find the dot product between any two vectors, they need to have the same number of components. But again, that's very important to notice here that, again, with my two vectors, I started with vectors, I did the dot product, and my answer is just a single numerical scalar. So, like I said, in my previous video, vectors are these mathematical structures that contain multiple values. And the vectors are, well, in terms of math and physics, they're structures that have dimension and they have magnitude or size. So if you remember back, we took this in my first video. If you have a vector composed of the scalars 4 and 3, we represent that either as kind of this matrix notation with the square brackets or as this arrow in space that points to the ordered pair 4, 3. The magnitude of the vector is its length, and considering it as kind of that arrow pointing is much more conducive to discussing the magnitude of the length. Now, to find the magnitude of the length, we're just going to use the Pythagorean theorem. And that magnitude, or that length, is denoted with vertical lines around it. So either the vertical lines like absolute value, because it turns out absolute value actually is the magnitude of that number. How far away is it from the origin? How far away is it from 0, right? That's what the absolute value really means mathematically. Or sometimes when we do vectors, we do the double lines just to denote that we're finding the absolute value of a vector instead of just a regular number. But again, we're typically just going to use the single set. So, like I said, if I want to find the magnitude of this vector, we have to turn it into a right triangle and use the Pythagorean theorem. So, Pythagorean theorem, a squared plus b squared equals c squared. Every student should know that at this point. So, we can also simplify that by kind of taking the square root of both sides. So I would find the square root by, well, 4 squared plus 3 squared, take the square root. The square root of 16 and 9 is 20, or, well, obviously you can see the square root is going to be the square root of 25, which is 5. The length of that is 5. It's your basic 3, 4, 5 triangle. So the magnitude of this vector is 5. And again, hopefully everyone can do the Pythagorean theorem. So like I said, I'll just go through that very quickly. The nice part is we can also extend this Pythagorean theorem into as many dimensions as we want to find the length of any vector. So even if I have this new vector v, which is 1, 0, negative 2, 5, this is a vector in 4 dimensions. It has 4 components to it. Okay, can you picture in your head a vector in 4 dimensions? What does a 4-dimensional arrow look like? Oh, yeah, well, we can't really comprehend that. Our brains don't work that way. Luckily, mathematics works anyway. We don't have to be able to necessarily visualize something in 4 dimensions to find the length of this 4-dimensional thing. This is not always immediately obvious because we're talking about a structure that we can't really figure out in our head, right? We have no context for what a four-dimensional arrow looks like. However, the mathematics still works. It is just the Pythagorean theorem. Square each of the components, sum them, take their square root. So how long is this vector in 4 dimensions that I can't possibly imagine? Oh, well, it's the square root of 30 long. That's how long it is. And that's really, really nice. Mathematics doesn't care whether or not you can visualize it because it still works regardless. All right. Now the dot product theorem. So the dot product theorem says that if you have two vectors that aren't zero, and there's going to be some angle between them. And again, think about any two arrows that you point out in space, right? No matter where you point them, there's always going to be some angle between the two of them. And the dot product theorem says that the dot product of those two vectors, which again is just multiplying the corresponding components, adding them all together, getting that single one numerical result, would also be the same as if you took the magnitude or the size of each of those individual vectors, multiply those together along with the cosine of the angle between them, bringing in a little bit of trigonometry. We could also solve for the cosine of theta so that the dot product of those two vectors divided by the product or multiplying their magnitudes together gives you that angle theta. Now, again, remember this works no matter how many dimensions we're talking about. Now, why would this be useful? Well, I can use this dot product theorem to actually measure how similar two vectors are. So in terms of data science and machine learning, if I can actually represent two different observations as vectors themselves, the dot product theorem will tell me how similar they are. So I can actually compare how similar two different variables are if I can represent them in this vector form, which again is a great application of using this new vector structure to answer questions that are not immediately obvious as to how I would normally answer them. And so, again, in this particular context, the closer together the two vectors are, the smaller the angle theta is. So the dot product gives us this really nice way of measuring how similar two different vectors are to each other. All right, but to wrap this up, really the most important part is being able to calculate dot products and understanding how we do that. Multiply the corresponding components and add them together. So for the conclusion, can you find these following dot products? Can you find the dot product of question 1 and question 2? And again, take the time to pause if you need to. Now, what I'm going to point out is that in question 2, I turned that first vector on its side. Still, the first component is still the first component. So the first component is still 1. The second component is 6. The third one is -9. You're still going to match them up. So in this case, the 1 and the -4, the 6 and the 3, and the -9 and the 0. You're still going to match up those components and multiply them together. Actually take the time to practice that and write that out. The reason I'm doing this where I'm turning it on its side is that once we get to higher dimensional structures, aka matrices, we're actually going to write out our dot products in this way. So make sure you can do that too. All right. Hopefully the computational part of the dot products wasn't too bad. And if you ever need to review the concepts as well, this is a relatively short video too as well. So as always, ask questions if you have them. And even if you do or you don't, please take care of yourselves.